Hello everyone, welcome to AstroStream, and today is our last episode with Dr. Reut Abramovich about the course Astrobiology, exploring the life in the universe. And you guys have been enjoying this session. I've been receiving your feedback, and I hope you enjoyed this last session and you sent us a lot of questions, and we'll of course love to answer those. So put in your questions in the chat box towards the right of your screen, and at the end of this video we'll answer those questions. So we are going to talk about, are we alone in the universe and what is the future of life in the universe in today's session. So without further ado, I'm giving it over to Dr. Reut Abramovich.
Hello everybody. It's good to see you. How are you? How have you been? This is our last session together. I'm kind of sad to say goodbye to you, but you can always visit me on my Facebook page, for instance. So I'm in astrobiology. I work at the Arava and Dead Sea Science Center. And during our last sessions, in more than a month, we actually covered quite a lot of things about astrobiology. And you can consider yourself very lucky to have successfully finished our mini course about astrobiology. It's been a wonderful time with you. Thank you so much for all your questions and all your enthusiasm. So just a quick recap of where we are, and I'll just share my screen here for a minute. Let's see. Sharing is caring. You know how they say that, right? So that's how it goes. Okay. So can you see my screen very well? That's okay?
Yes, that's
so. Perfect. Today we're going to talk about a great topic, and that topic is the future of life in the universe. Are we alone? And it's not only about the future, but it's also about the past, the present, and how the universe in general works when it comes to life. When we talked about astrobiology, and I encourage you to go through our sessions before, we talked about the origin of life on planet Earth. We talked about its evolution. What are the common elements? What is a habitable zone? How did life begin? Did they start as a DNA? How were the first protein made? We talked a lot about these things. We also talked about what kind of technologies can we use today. So we know there is some sort of a consensus going on what is a life form and how we can detect it and realize that it is a life form. And we talked about the different technologies that we're using today. Remote sensors, remote satellites in astronomy. We're talking about underwater robotics, which are pretty big in marine microbiology and marine biology in general. And we talked about why we should search for life. And we did a very thorough, basic overview on the basis of astrobiology. So today I'm not going to go through all these things, but we're going to talk just about life in the universe. Is there life out there? Is it intelligent? What are our chances of even finding them? That's an exciting topic. So mostly we are very familiar in how aliens are introduced to us via, popular TV and films and other media in a popular culture. So this is an example of how usually we think about aliens when we see them, when we think about them.
Incredible. They should have been destroyed by our lasers. It's not even registered on my tricorder.
Absolutely. Doesn't even look real.
It's not life as we know or understand it. It is obviously alive, it exists.
And it can bear up under full phaser power.
And I suggest we risk taking it aboard.
It's too close in here, maybe a trap. Let's move on.
So basically, this episode has dealt with and showed us what we think alien might be. And Star Trek, the original series, had a lot going for it from a technical and scientific point of view at the time. They did a tremendous job. And the questions here are really good questions. What do we think about it? The aliens are going to look like us? No. Can we detect them with our technology? I don't know. What size, what shape, what color? Is it intelligence? How does it work? So there's many, many questions. Where will they come from? Who they are? And this is a really normal representations of alien in our society at the moment. So bear in mind that the life we look for might not necessarily look like what's happening in the Star Trek series and in the Star Trek world. If we go for a quick recap on some of the facts that we know from our scientific analysis and what we know on planet Earth. So we know that the Earth has formed about 4.5 billion years ago. We know stromatolites, which are microbial communities which build rock, have been found in 3.7 billion years old rock. So basically very close to when the Earth has formed, maybe 500,000 years or 1 billion years after the Earth has been formed, we see evidence for microbial communities arising and working and changing the geological structure and the atmosphere of the Earth. We're looking at fossils. In the fossils records, we find big creatures only about 600 million years old. So if you took the whole Earth history and you look at how much, of it are like big creatures, what we might like to find in other places like aliens and dinosaurs and whatnot, then actually they're only 600 million years old. And actually, if you look at the entire history of planet Earth, the existence of humans alone represents 0.04% of the entire time the planet is around. So we're not that common, actually. When you look at the 5 billion years old and how much intelligence is part of that history, it's a very, very tiny part of it. When we look at microbial communities on planet Earth, we can find them in extreme environments. It's very rare that we find other life forms. We find some insectoids, we find some, we talked about tardigrades, about water bears, that they can be found in extreme environments and in other environments as well. But the majority of extreme environments, whether it's high salinity, high pressure, very low temperature or really high temperature, complete darkness, for instance, radioactiveness, we find all these areas which are very lethal to us. We find thriving microbial communities and sometimes whole ecological systems, as we've seen with the discoveries that Alvin, the submarine, has found since 1964. So what we're looking at is that in the last decades, not years, but in the last decades, I would say maybe from the 1960s, we actually do see big technological advances in finding life forms in extreme environments and also in our capabilities to look outward to the big universe. So all these are really good signs that we know a little bit about how life have evolved of this planet. And we keep wondering what happened to life elsewhere in the solar system and in the universe. And what can we learn from what we know now on planet Earth? So when we start about where is life in the universe and how does it look, where is it, when was it formed, we have to take in consideration the fact that we know about our physical universe. We live in a galaxy, one of many, many galaxies in the universe. In our own galaxy, there are 200 billion stars. Okay, that's a massive amount of stars, and around not most of the stars, but around a fraction of those stars, we find planets. So it's very interesting for us to understand how much from those planets can actually be a good place for life, like planet Earth was. If you look at the Milky Way from a size point of view, then the length of the Milky Way is about 100,000 light years. One light year is about 9.4 trillion kilometers. That's pretty big number. So the space we're talking about is a really big space when we talk about the distance. And when we talk about light years, we actually talk also about the time. A light year is the time that it takes a light ray, right, to cross the distance for 1 year, 365 days, per our own agenda of how, planet Earth revolves around the sun. So we're talking, if we're looking at something and it's 20 light years away from us, it means that we are now seeing the light when it exited those stars 20 years ago. And if you talk about Hubble and other new telescopes, they estimate that the age of the entire universe is about 13.5 billion years old. And as we have better telescope, we get to the edge of the universe and we think that we see light even from even more distant stars. And the age of the universe can be older. But there's an issue here of not only a gigantic area of space and kilometers in length that those stars are away from us, but also the matter of time and how much time has passed since we looked at those stars. And when we look about exoplanets, and I said something about that, and I talked about TESS and Kepler in my former lecture last week, is that we talked about exoplanets. An exoplanet are planets around a star, not necessarily a star like our sun, but it can also be a white dwarf or a red dwarf or something, or a binary system. And this planet, we say it's an exoplanet, that it's an Earth-like planet because it sits in the habitable zone. It circles its sun, or it circles its star in an area which would be a good place for liquid water. If there is water, they would be in their liquid phase due to the temperature regime that we found through our analysis. So this poster is a bit old. It's from 2013, but it already shows you how Kepler found exoplanets. And most of the exoplanets which were in the habitable zone, Kepler deduced they would be gas giants, actually, while the minority will be terrestrial and will be smaller. Now, with the TESS telescope coming up, and with the TESS mission, which was just finished a year ago, or I think it's this year it has finished, we started analyzing, we're going to see much more planets, which are exoplanets. They're in the habitable zone, but they are terrestrial, and they're in relatively closer proximity to planet Earth when we're talking about light years away. So we have 1,000 confirmed exoplanets in 2013. And when we look forward today, we actually have more than 5,000 exoplanets. But we started with having 200 billion stars in the Milky Way. And now we just have about 5,000 exoplanets. And let's say with TESS, we'll get to 6,000 exoplanets. It's a big magnitude difference between the many stars that we have in the Milky Way and to how much habitable planets might be out there. If we look, for instance, on the top exoplanets that are closest to planet Earth, we can see that Proxima Centauri b has its period around its sun, around Proxima Centauri, for about 11 days, but it's about 4.2 light years away. And in light year, which is such a huge distance, remember, so 1 light year is 9.4 trillion kilometers away. It will be very hard for us to actually go with a human crew and check what's going on. We're going to have to rely on instrumentation. The other closest stars so far that we have discovered through the Kepler mission and through TESS are Gliese 667cc and Kepler 442b. So, these planets correspondingly are 23 light years away and more than 1,000 light years away from planet Earth. If you want to take the whole planet Earth that we know today and to put it one after another planet Earths in order to do 1 light year away, you're going to need like 720 million planet Earths in order to do this distance away. It's a massive for 1 light year. It's a really, really big space for us to find it. So those are the 5,000. So those are the closest exoplanets that we know about, and we know now about 5,000 exoplanets. So where are all these life forms? What's happening over there? So when we talk about life forms, we really, really like to talk about the Drake equation by Frank Drake, an American astronomer who was the founder and also former director of the SETI Institute, the Search for Extraterrestrial Institute. And he, in the 1960s, during a conference, he decided to sort of concise all the topics in that conference in one equation. And the point of this equation wasn't to quantify the number of, civilization or the number of aliens or the number of life forms that we can find in the universe, but it was more a way to sort of like put the lid on and to put a frame so we can talk about this with the public and show how we can do science communication and talk about these issues of aliens and life forms elsewhere in the universe, because we want to know who they are, where they are they there, what are the chances of us meeting there, how many aliens or civilization can be out there. So n is the big number that we're all looking for. And some of these probabilities that we need to focus on and to understand is that we don't know them. These are just the framework to make a guess and make a very nice guess, but it's not a very scientific guess at the moment. So for instance, the first factor R, it's the average star formation rate of the galaxy. How many stars are formed in the galaxy? And today we have more data on that from astronomical and astrophysical analysis. FP, fraction of star with planets, because we think that life is going to evolve only on planets like planet Earth. And then, of course, you have the additional factor like NE, the average number of planets per star that could potentially support life per star observed to have any planets. So what if we have a solar system or something look like a solar system and they have 8 planets? So is it 1 planet out of the 8? Is it 3 planets out of the 8? How many planets per star could potentially support life? And I remind you that even in our own solar system, we don't know yet, aside from planet Earth, if there is life anywhere else. FL, the fraction of these planets which could host life, that actually develop life at some point. So we have here a distinction between planet that could potentially support life, like planet Earth, but not only just potentially, that they actually develop life. Again, we have no clue about these planets. The exoplanets that Kepler and TESS have been reported, and also ground observation telescope, they're saying, okay, planets sitting in the habitable zone. They're good for this factor called NE, not for factor FL. We don't know if they actually develop life. The other factors are Fi, the fraction of these planets that develop intelligent life, Fc, the fraction of those which developed intelligent life that release signals that could, in principle, be detected. And what are these signals? The only signals we now aware of that can do this massive interstellar voyage are electromagnetic waves and laser waves. And either of those, we haven't really detected anything that would indicate that there is a life form or intelligent civilization out there. But these are the signals that we today only can actually say that we have radio telescope, we have the technology to detect them. And L, the final factor, the average life of an advanced civilization, or how long a civilization survives once it develops technological ability to transmit signals. Again, we have no data whatsoever. How long will a civilization survive once it develops the technological ability to transmit signals? So this is all a very interesting mystery to work with. The beauty of it is that today we have new data that can simplify the way the Drake equation works and can give us good numbers to some of the questions arising from it. So I'm talking about a concept which is called the Astrobiological Copernican limit, and it has been published in 2020. And what we're looking for is that we're saying, okay, we now have data and historical data from astronomical instruments, from microbiology research, right, extremophiles and so on, from the SETI Institute, but also from other space missions. And we can incorporate this to get a range of probabilities for the Drake equations. I mean, we want to know if it's really intelligent to get, if it's really a strong signal for us in the Drake equation and we can find plenty of planets, or whether we want to, when we look at the data, where we're thinking, okay, maybe the model needs to be a very weak model and saying, you know what, we're not going to have intelligent life forms, but we are going to have microorganism, like simple life forms, because we know that on planet Earth, most of the time on planet Earth, we had microorganisms and very simple life forms. We didn't have any intelligence whatsoever. Only about 0.04% from the time of planet Earth history do we have humans, do we have intelligence. So let's take that into consideration when we're looking at the new Drake equation and when we're looking at finding other planets in our universe that can actually harbor life and might have intelligent life forms. So the basic assumptions for this limits is that life will evolve in similar terms as on planet Earth. It will take about 5 billion years. We're looking at a metallic-rich star. It's very important to have all the different chemicals that we talked about. And the development of our own intelligent life, we think the basic assumption for the astrobiological Copernican limit, we think it's not that the development of intelligent life is not something unique It's not something special. It just takes a really, really long time, and it takes the resources that we've spoken of before in our prior lectures. So another question that this model is taking into consideration from the Drake equation is, how long will it take us to reach or get signals from other civilizations? Because if you recall, we were talking about light years and light years away. What happens if some of those planets are so far away that it will take thousands of years for us to detect their signals? Does it make any sense that we will detect it? Where we will be 3,000 years from now? We were in such a different place 3,000 years ago. So where are we going to be 3,000 years from now? How are we going to deal with that? So this model, and I'm just giving you the final summary of it, and you can look at the reference, the original reference. It's published online and it's open for the public. Is that when we look at, there's a range of categories where we can look at, and then we can realize what is the number of civilization that are in the galaxy. And when we look at ultra weak categories, okay, which we say there's only primitive life forms, then the minimum number is in the billions. We have billions of civilizations, okay, which are not civilizations because they're just primitive life forms. But the nearest neighbor star for it is 7 light years away, okay? The maximum is 7 light years away. It's going to take us ages to get there. At the moment, we don't have even propulsion system to get a human crew in a feasible time to that star or to its neighborhood. Okay, and the minimum time search before SETI detects signal is of course not available because these are primitive life forms. We're not expecting them to put any signals out. When we look at moderate categories, and in moderate categories we change the time frame. Okay, we say, okay, there are communicating extraterrestrial intelligence civilization, but they can only exist within a time frame of a 2 billion years window of opportunity. Remember, we take examples from our own planet and we put them on the data. So, and we expect that the stellar system would be the age between 4 to 6 billion years, because we're trying to narrow down the area of opportunities where we can find these intelligence life forms. And this, in the moderate category, then the minimum number of civilization in the galaxy are only 72. In our entire Milky Way galaxy is 72. That's the minimum number, and the maximum is around 250 or 300. Everything here has a big uncertainty range around it, and they say so in the article as well. The maximum distance to the nearest neighbor in light years is 11,900 light years away, with a minimum of 6,000 light years away. Again, it's so unfreakingly far away. We have no way to get there. We have no way to reach the light speed. If we send a radio signals, it goes in light speed, and we have no way to go beyond or to find a way to bypass how long it takes with the light year to transmit an electromagnetic wave. That's the speed. It's the speed of light year. It's the speed of light, 3,000 kilometers per second. Minimum expected search time before SETI detects a signal from moderate categories is about 2,420 years. So basically, we are again looking at a problem that our generation time of human species and of our culture, even if you look at empires, nobody is really good at having an empire for 3,000 years or so. I know some cultures have that, but it's a very rare case, and it makes it very difficult for us to understand how to cope with signals coming with such from alien civilization that are so far away. And if we're looking at even stronger categories, that we narrow the habitats, that the age has to be between 4.5 and 5.5 billion years old only, we're really narrowing down the time and what type of stars and everything, then the average lifespan of this civilization is only maybe 100 to 1,000 years, then we get only 36 civilizations in our galaxy. And they're completely far away, and the search time before SETI detects the signals in only 3,060. One of the reasons the time is so far away is because of the way SETI is also collecting the data from the universe. There is an X amount of radio telescope with SETI that are covering only a very small fraction of the sky. And because we're dealing with technological limitation, and we're dealing with such a small portion of the sky. That's why it will take also so much time until we detect any interesting signal, because we're not covering the entire sky, and we haven't been covering it for very long. SETI is not here for 100 years. It's a lot less. So all the data and everything, when you look at it, there's a big technological problem in estimating. Not in estimating, there's a big technological problem actually contacting these civilizations. There could be civilizations, there probably are civilizations, and more certainly there would be primitive life forms a lot more than civilizations, because that's how we learned it from planet Earth, and that's how the data points to. But our chances of actually getting in contact are so slim. They're impossible at the moment. And people are trying all the time to bypass some of the aspects here. And that's a completely different discussion that I'm not going to go into. But, let's talk about some time concepts. So I don't know if you're aware, but there's a jellyfish called Turritopopsis dorni, which is biologically immortal. It never dies. It never dies. If it's sick, if it's injured, then it goes back, it reverts its age back to a ball of cells. And then it starts growing again with the different stage of a medusa life in the life cycles, going from benthic polyps to ephyria to medusa to gametes and planea larvae, so planula larva. So it has all these life stages, but the minute something bad happens, that it just reverts back to its former stage. It just goes through cycles in life. It never dies. If something never dies, it has no mortality concept. Does it have a time concept? What would happen to a civilization of entire beings that never die? What kind of time concept would they have? Would we be able to communicate that? I mean, we're so dependent on time and our mortality, the way we do politics, the way we choose our mates, the way we live our lives. How can we deal when we don't have enough time? How can we deal with these massive universal time frames that I've just spoken of? So it's pretty interesting. So time in our universe, what I'm trying to say here is that time and space, the area is so vast, and this white arrow in the middle is just us in 2020 trying to figure out our universe and find life. We're really, really at the beginning of understanding how to find life elsewhere and what kind of technologies we need to in order to do that. And we're realizing that we're in a really big universe and a really big time scale. And our species is very short-lived in comparison to that. So it's a big issue how you're going to find those aliens. What are they going to be made of? Do you have the right technologies to detect them? Are they going to be based on nucleotides? Are they going to be based on proteins? Are they going to be based on anything else? We have all these discussions. But the point is that currently, according to the best data that we have, our chances of actually contacting an alien life form, intelligent-wise, for sure, it's impossible. Unintelligent-wise, all of a sudden, you have a completely different ball game. That's a much feasible thing to do. So what do smart people think about life in the universe? And this is a great talk, very short, by Carl Sagan. I think he's one of the best scientists ever to come from the United States and explain to the entire public and make a mark about the universe and its possibility. He was an astronomer, an astrophysics, and astrobiologist. He wrote marvelous novels as well. And if you haven't seen Cosmos, the original series, you might as well take a peek at it now at YouTube. It's a wonderful, wonderful piece of science TV. It has been the basis for my exploration, for my passion for space as well. And this is a very brief conversation with him on American TV. So enjoy this.
That's inevitable, that humans would project their hopes and fears upon the cosmos. The standard Hollywood attempts are to portray the extraterrestrials as red claw and fang, pointed heads and nasty dispositions. E.T. and Close Encounters of the Third Kind, to show the possibility of benign extraterrestrials, but even there, the extraterrestrials are only slight variants on human beings when the evolutionary record is clear that extraterrestrials would be very different from us. And also, they're not awfully smart. These extraterrestrials.
Sweet, but not smart.
Sweet, but not smart. If you look at timescales, you realize that our civilization is the most backward civilization in the galaxy that could communicate at all, because we've just invented radio telescopes just a few decades ago. We had not the ghost of a chance of communicating with anybody else. So if we receive a message, it can't be from anybody less capable than we, because anybody less capable can't communicate at all. So it has to be somebody much in advance of us, and maybe as much in advance of us as we are in advance of the ants, say, or the worms.
You, Carl Sagan, scientist, astronomer, enlightenment, you think that indeed there may be some sort of intelligence out there?
May, surely may. We now realize an enormous number of planets, a range of planetary systems around nearby stars. So there's a lot of potential abodes for life. That's one thing. Then there's the question of organic matter. The carbon-rich complex molecules that are essential for the kind of life we know about are fantastically abundant. They litter the universe. We see them in asteroids and comets and moons in the outer solar system, and even in the cold, dark spaces between the stars. So the stuff of life is everywhere. And then there's time. There are billions of years for biological evolution on all those worlds. There are many worlds that are much older than ours. So you put those together, lots of places, lots of organic matter, lots of time, and it seems very hard to believe that our paltry little planet is the only one that's inhabited.
You know, I was afraid to use it about Earth people, us, we, are so benighted. The Earth is the ghetto of the universe. We're the ghetto of the universe.
Well, in an extremely backward and obscure part of the Milky Way galaxy, we're 30,000 light years from the center of the galaxy. We're in the galactic boondocks. This whole galaxy is only one of probably hundreds of billions of other galaxies. A useful calibration of our place.
There's also religion in science.
There is a tendency in both schools of thought to think that they have a corner in the truth. I mean, a way to look at it is the following. Science and religion on some level are after the same thing. Take the question of our origins. Both science and religion attempt to approach this question. But the religions all contradict each other, so they can't all be right. The Judeo-Christian Islamic religion holds that the world is about 6,000 years old. You just count up the baguettes in the Old Testament. It's very clear, 6,000 years old. The Hindus have an infinitely old universe, with an infinite number of creations and destructions of the whole universe. Now, those two major religions can't both be right. How do you know which is right and which is wrong? Well, the only way is to appeal to the natural world around us. And the natural world around us shows that the Earth, for example, is about 4.6 billion years old, nothing like 6,000 years old. So a literal reading of the Bible simply is mistaken. I mean, it's just wrong. It's just wrong. As a work of science, it is flawed. It's the science of the Babylonians in the 6th century BC, and we've learned something since then.
This special episode of Blank on Blank is supported by Squarespace. Whether your story is out of the ordinary.
Hi, thank you. It's me again. So we had this beautiful talk by the wonderful, amazing, sadly not with us anymore, Carl Sagan. And he very eloquently put it out there that, yes, he believes there's life out there. Definitely, the universe is so huge, everything. You have the nutrients, you have the time, you have the places to do all this life and to make life evolve, just as it happened on planet Earth. However, our ability to contact those life and make science with them, that's where we currently lack as the human race. And I stand with Carl Sagan on that, and I'm looking forward to find our new things. And when we're looking closer to our place, when we're looking closer on the solar system, we do find that there's many places that can inhabit life and that we should investigate. So, for instance, on Mars, we have now a rover on its way, and we know for a fact that in its first billion years, Mars was very much like Earth. It had broad oceans, about 6 meters depth. It had an atmosphere. It had water definitely going around. So now we're looking with the rover Perseverance at the Jezero crater in order to understand whether life has evolved in the first billion years of Mars, whether perhaps we can find something that looks like life on planet Earth in its first billion years. When we look at Jupiter and the other gases, someone is honking. Now it's good. When we look at Jupiter and the other big gases planet in the solar system, then we find some contradiction. We don't expect at the moment to find life forms, not even microorganism life in Jupiter or in Saturn. But for instance, when we look at Neptune and we look at Uranus, then we did find some plumes coming out of oceans beneath the surface of these. There's some water molecules coming out from these planets. So we want to send more, we definitely want to send more equipment and technology that we have already today to these beautiful planets in order to understand what's going on. The moons of some of these planets have very interesting characteristics that we think life can be there. So for instance, Jupiter Europa, the icy moon, has very interesting liquid ocean, very salty, underneath 5 kilometers length of ice. And we would love to go and drill there, but it's a really hard technically to do. To survive that mission, it takes about 8 years just to get to Europa. And because of the radiation and the strong magnetic fields arising from Jupiter's activity, then we're going to have a big problem taking care of our equipment once it's got there. So it's not an easy solution. Titan, which is the moon of Saturn and the only one with a thick atmosphere, has probably some very interesting liquid lakes and liquid oceans of, I think, methane, if I recall correctly, because the temperatures are so low, then you have a completely shift of what we are used to from planet Earth, and we have a shift to new chemicals, having new types, not types, have new, whether they're liquid, gas, or solid, they're moving into a different state. Yeah, I think different state. So I'm looking forward to all what we can find in our own solar system. And I think Venus now is becoming more interesting. They found phosphine, and they seem to say that phosphine could be a sign for life forms, because we know phosphine can be generated both by anaerobic life forms on planet Earth, but also in a chemical way. So we want to first have more ground truth observations of Venus to find more phosphine and make sure that it's really there. And for instance, on Mars, if there are underwater lakes, if there are caves are a wonderful place for life to evolve and to sustain and be protected from high radiation and other things, then we should go and we should check. But just imagine how hard it is to find even simple life and planets in our own solar system. How hard is it to find life elsewhere in the universe? It's a very hard task. And moving forward, and lastly, so we started the series with asking why search for life. And we've spoken and we talked about so many items. I think we're searching for life because we are built to search for life. We have an affinity for it. That's what we do on this planet, and we do it very well. And to ask such a question, why search for life? Yes, I can give you a number of reasons, because we can help us understand our own story, because we can find some medicine, we can find some technological application. But you see how much energy we have put into the science, but also into popular culture about life elsewhere in the universe. Then I think it's about time we understand that it's in our spirits to go and search for life elsewhere. It's a fundamental thing that we have to do, and that we will always do, and we will continue to discuss on. So I want to thank again Shweta and AstronEra for their wonderful opportunity to do this series with you. And I'll see you around in the universe. Thank you very much.
Thank you so much, Reut. It was really great having you talk about astrobiology, and the sessions, each and every one of them, have been really amazing and really insightful and really advanced.
Thank you.
I mean, this is a certificate course, and we surely are going to give out certificates to everybody who's been attending. I see that there are at least 20 people who have attended the course right from the beginning and have stayed there. We have few people like Adarsh Kumar and Rupa Dhawale ma'am, who has always been there asking us so many questions. Also Nirmal Gupta has joined a lot of times, and There is Sanika Jogipetkar as well. I'm just taking out these names because the energy of these audiences, keep us both going. I think you'll definitely agree to that. So today we don't really have many questions, but I see a few, and some of them are not related to astrobiology, but I'd still like to go ahead with them if you don't mind. So
Sure.
Adarsh Kumar is asking, how do you start your day and what research papers do you refer to and make conclusions? Also, what kind of gear do you use?
What kind of gear do I use? At the moment, when I go out to the field, I have many types of gear that I use depending what type of field work I'm doing. In the lab, I have a regular molecular lab that I have to work with. Regular molecular lab, you have a centrifuge, you have a microscope, you have a PCR machine, you have a lot of pipettes, you have a lot of glassware, typical lab thing. When I go to the field, I usually have a lot of other things. Some of them are pretty basic, just to make sure that I survive in the field. And I'm sure you know the feeling, Shweta.
Mhm.
And how does my day look? So we are under constant lockdown now in Israel because of the COVID-19 situation. So I'm actually not going out so much as I want to. And I'm having a great time with my family. I'm trying to work out. I call my mom almost every day to make sure that she's happy and, that everything is fine with her, and my dad as well. And that's about it. My days are pretty boring by now. What is that I have found out that I am doing a lot more Zoom sessions and online sessions, and I'm in a lot of virtual conferences that I have to participate in. So it's busy, but it's different type of busy. Yes. Thank you
I
for your
can
question.
imagine. Yeah. So there is a related question by Adarsh Kumar. How does the Drake equation came into existence? Like the way in which we define every term, especially the term FC, which we determine whether the CIV is type 1 or above.
Okay, so hold on a second. We're going back to that Drake equation, so we can be more focused on your question. One moment. So the question was about FC, the fraction of those which develop intelligent life that then release signals that could, in principle, be detected. Is that the question?
I think you can read that. Even I'm not quite clear about it, but if you can read that, maybe it's quite in the beginning of the chat.
Okay, so Frank Drake has a wonderful paper in Astrobiology magazine, like a year ago, maybe not very recent, in which he revisits how he came up with the Drake equation. And it's very simple. He had a conference for SETI in the 1960s. I think it was maybe 65 in Chicago or Boston or something. And him and the review panel had all these topics all of a sudden popping up about how to find life elsewhere, and they had all these different angles at looking at it. And they decided to make it to do the headline in order to summarize all the different talks and to make it look much more professional. They decided to make it to an equation and make sure this equation is the multiplication of probabilities. How much of this and this is, then we'll get some sort of an answer to how much civilization could be in the universe. And at the time, that conference was a very far out kind of concept, very basic, thinking out loud, and all the different aspects of what does it mean to find life in the universe. At the time in the 1960s, we didn't know much about extremophile. We didn't know much about stromatolites, I think. And so what happens is that nobody realized that the majority of life on planet Earth was actually microorganism to begin with. And everybody is so penned up on looking at, finding someone else as sophisticated as we are in the universe. So that's the issue. That's how the Drake equation came up with the conference. There's a lovely, you're welcome to look through Google Scholar and see his latest writing by Frank Drake. He writes very lovely about that period. And it's interesting. It's a very interesting read, in my opinion. Yes.
Mm-hmm. Okay. So we have question by Miss Nirgude. She has written it quite vaguely, but let me try to put it in a different question. I think your screen is doing something funny. Can you stop sharing your screen? We can see your YouTube.
Sure.
Okay.
You can do like this.
Uh-huh.
And then continue. Yes,
okay,
very good.
Perfect. Yeah. So she's asking, how can we reach the planet Keplers? I think that's what she means. We travel in speed of light, then how much time will it take? Well, do you know how much time would it take for us to reach to the closest exoplanet, the planet that has been found by Kepler?
Great question. I was preparing for this talk and I was looking into propulsion systems because I wanted to nail that answer. And then I got completely confused. So here's the thing. Our current propulsion system, the best one is called electrical propulsion or ion engine. And we used it on Voyager 1 and 2, which are spacecraft, which are already outside of the solar system. And, took them a while, but they're like apparently the fastest vehicle we ever sent. So the closest exoplanet is the Centauri B. It's about 4.2 light years away. A light year is 3,000 kilometers per second. Sorry, the speed of light is 3,000 kilometers per second. And you need that speed in order to get to there in 4 years. We are not even close to getting to the speed of light. Our speed is currently 0.05% the speed of light. So you're going to have to do the calculations yourself, but it's not that hard. And basically just multiply how long it's going to take us. It's going to take us forever to get to Alpha Centauri B at this time. I mean, just think about, so it's only 8 minutes of light between Earth and the sun. And it takes us 6 to 9 months to get to Mars, which is nothing. Yeah. So it's going to be a really, really long voyage. I'm going to go and guess around 1,000 years.
Mm-hmm. Yeah, I can imagine.
So one of the interesting things which I haven't put in my presentation is called, there's an initiative called the Breakthrough Initiative. And one of the things that people are trying to do is basically lower the mass that you want something to send, for instance, to an exoplanet. If you lower the mass, if you reduce the mass of what you're sending significantly, you can push it perhaps with a very strong laser beam. Mm-hmm. And with a very strong laser beam, you can get it to be really fast, almost as close as the speed of light. And that way you can shorten the time. Now, the question here, there's two questions. First of all, I haven't seen any engineering plans, worthwhile, any publication, anything working that even close to be working, a working prototype of what I'm talking about. That's me. But the second thing is that if you reduce the mass so much, what's going to be on that sensor? How is it going to communicate back to planet Earth from 4.2 light years away? What is it going to tell you? Are you going to be able to say anything significant if you reduce to a really, 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 really tiny chip? So it's an engineering, but it's a very creative and original thinking on how to bypass the problem of light speed. You just reduce the mass and you send something with a laser. Mm-hmm. Good luck with that.
Exactly. I mean, it should have some devices that will help it communicate back to Earth. Otherwise, it is of no use. Even though it finds out something, if it reaches there and it cannot communicate with us because we have to keep low mass, it won't be of any use for sure. Yeah. Okay. We have more questions. Okay. Again by Nirgude. What kind of atmosphere does the jellyfish need to survive on this? Don't need any atmosphere? I'm not quite
the jellyfish?
Yeah. Mm-hmm.
No, the jellyfish is found in a lot of temperate oceans. It's very common in all our ocean. It doesn't need any extreme environments.
I think you mentioned about the jellyfish Turritopsis duruni, which never dies. Then if this
never dies.
Yeah. Okay. So Nirgude is asking question that you said that it never dies. Then if it doesn't die, even if the universe ends, then it won't die. I think she's she's trying to ask you that. Mm-hmm.
That's a great question. It's okay. It's a good question. I'll clarify what I was saying. When it's in the ocean, it has a lifestyle, which means it never dies. It can sustain itself in the ocean for eternity. That's the thing. It changes its life cycles. In a lot of marine invertebrates and in marine mollusks and otherwise, they have changes of life cycle. You know how a butterfly changes from a larva to a butterfly and so on and so forth? So we find these different types of life options with different marine animals. So the jellyfish is one of the examples for that. So as long as it's in the ocean, it can change its reality, it can change its own state and go back to when it was a very young cell or when it was a very young larva. And then it corrects itself and then it grows again to it happens only when it's in the ocean. If you take a jellyfish out of the ocean, then it's dead.
Mm-hmm.
It just cannot do the things that it do. Is really big. You can always kill something. I'm just saying that while we die naturally because our body ages, and that happens in a lot of places on planet Earth, if a tree gets hurt, the tree will try and fight it and will try to recuperate. But a tree can it will die. With this larva, we find this tactic of going to a different stage in life and prolonging it and going through all these life cycles all the time with the same DNA, which is amazing.
Okay, I get it. All right. So Nirmal Gupta has an interesting question. Are we afraid of intelligent life from other planets? If yes, then why we are developing artificial intelligence? I'd like your take on this.
Someone has been watching Star Trek. So there are two different questions here, I think. One is, are we afraid of intelligent life elsewhere? I'm not afraid. Other people are. I think Stephen Hawking, the great physicist, said that it's a stupid thing to go and search for, like to actively pursue other civilization to notice us, because they're going to be so much more advanced. Just like Carl Sagan said, that if they're so much more advanced, then there's no way we're going to benefit out of it. It's just going to be completely out of our scope. So we shouldn't go and look for alien life forms in an active way. But that's Stephen Hawking's thoughts and ideas, and he's a great man. Other people are really happy to go and check out what's happening. For me as a scientist, I'll be delighted to find other life forms, just to say that whatever I think how evolution happens and the restrictions of physicality on it, that it's a normal process that goes elsewhere in the universe. I don't think it's a big issue. And the question was about artificial intelligence. So it's a completely different topic.
Yeah.
Other civilizations could be super advanced and not have robots or not have artificial intelligence anywhere. Yes, there are a lot of dangers in artificial intelligence. I agree, but it's a completely different discussion. I don't think it has to do, like, it's a popular discussion to do about what is artificial intelligence and when Skynet will become, consciousness, and what is space. Elon Musk, CEO of SpaceX, is doing with this company, which is called Neuralink, and other people who are talking about singularity, the day when all our physical beings will be meshed into, the internet or into a digital format, and we won't be living here anymore in the physical form. Great science fiction books deal with that area. I don't know what I feel about it. Don't know. There's so many.
Yeah, even I don't think I'd be able to comment, because one side it is really great for our development, and on the other side it is also in a different manner. I mean, there are of course two sides to the coin. So us scientists are still, like, we are aware that there are two sides of the coins, but when we are doing some research in our own field, we are obviously aware of that, but I don't know if we'd be able to comment on this. So Parth is asking, how can we design equipments that can sustain extreme environments on other planets for detection of life?
So NASA has been doing that very successfully for decades. And usually what they do is that they have JPL, who are great engineers. They have NASA Ames Research Center. You should all apply for internship in NASA if that's what you really want to do. You should check it out. Another place to check out if you really want to do space exploration is what I talked with you, Shweta, about, is about the International Space University. And basically what you do is that you start with they have a huge matrix. I've seen this. There's like this huge page, a matrix, which starts with a scientific question. What are the goals of this scientific questions? How do you measure the outcome of your hypothesis? Because they're looking to have quantifiable outcomes from their equipment. They're not looking for just a general, it looks like. They really want to know how you're going to use the equipment, what kind of measurements you're doing it in. You have to specify it, with micrometers or with intensity, or find exactly the measurements, the physical measurements with which those instruments give you the output that you're looking for. And then, they start asking you, okay, what kind of equipment do you have today that does this? What is its range of operation? Some equipment is very sensitive, so you cannot just off the shelf send it to a place which is minus 80 or minus 200 Celsius degrees. You have to do modifications. But then usually what happens is that the engineers in JPL and in other NASA centers, they come up with their own solutions. They have a lot of background into what will survive space, what will survive landing, what will survive these tough conditions, whether it's Venus or Mars or the moon, and they build it up from scratch. So some of the best inventions come from NASA engineers because they know how to do this amazing high-rise camera, They usually now work with MIT and with other universities which also have really strong engineering capabilities. It's pretty awesome. And then sometimes, not often enough, they try and test it outside here on planet Earth. So usually what happens is that they have very specified chambers, let's say like a Mars condition chamber or a moon condition chamber, and they emulate some of the conditions that the equipment will encounter on the moon, on the Mars, or elsewhere, but not all of the conditions. So they check different sections to see how this equipment works, if it works well, if it's anything in the software, if there are bugs in the software, in the hardware, things like that. But very, very, I would say too rarely do they actually go and do the extra mile of literally taking the stuff and put it in Antarctica. Okay? Sometimes it's just too much money and too much time to put into the process, and they feel much more secure to check it with their own equipment in their own laboratories, like I said, in all these different chambers and things like that. Anything that is sent to space today goes through a really, really rigorous testing at different companies. They go through massive shakes because, doing the launch and the landing, everything shakes pretty bad, and then they get bumped and they get cracked, and, there's a lot of physical torture that these things are going through just to make sure that they're able to survive the journey, let alone do the math and do the science. Yeah.
Physical torture for the equipment and mental torture for everyone who's working on those equipments, right?
Yes.
Yeah, okay. So we have another question by TP Shade. Can that jellyfish's cell survive in extreme condition or with water? And after some time, if it occasionally comes in contact of water, it might start its generation again.
So that's a great question because it's very specific and it's written very nicely. It talks about hibernation. So, for instance, we know from tardigrades that if they dry out, then they go into hibernation. If you put them afterwards with a drop of water and they start reproducing again, and they're just as fine. And the question here is about the jellyfish. And the correct answer is that I don't know. I'll have to check. But I don't think it works as the tardigrade. I think they really, really completely dehydrate, and they're not able to withstand the situation of dehydration as in contrast to the tardigrades, but we need to check that out. Okay. We can find in the literature.
Yeah. All right. I think those are all the questions that we have had today, and everybody of us who have attended all of these sessions have truly enjoyed them and have learned a lot. So I'd like you to tell everybody about the upcoming talk that you're going to have at the Mars online. Yeah.
Yeah, okay, just very quickly. So there's the International Mars Convention happening this week. You can go to the website of the Mars Society and register. Everything is free. It's online. There's amazing talks for like 3 days with people like Jim Bernstein, the director of NASA, is going to give a speak. There are many scientists from NASA that are going to give updates about the rover, about their science, everything that. Robert will give a few speeches as well. So register to it. I have been invited and I'm very happily accepted to be on a panel talking about the search for life on Mars, together with Dr. Chris McKay from NASA Ames Research Center and Dr. Carol Stalker from Research Ames Center. Both are like mega scientists in this field. It's a big honor to be on the same panel with them. We are going to be moderated by a very well-known outreach professional from the Mars Society. And it's going to be this Friday. You need to check the time zones because for me, it's going to be in the morning. For them, it's going to be 7:30 p.m. So just check, please check the website for the Mars Society and check for their convention. And I highly recommend it. It's just, I remember it from last year. It's been a blast. It's really interesting. And it's the best information there is.
I can imagine having you on board. I'm really excited to hear from you and everybody else, and I have already registered and I'm looking forward to this. It won't be a big time issue for us because if it's a very early morning for you, we are just 3.5 hours ahead of you. So it's gonna be like perfect time for us. In the morning we wake up and log in and watch the sessions, and it's going to be an absolute blast hearing you there as well. So just few announcements from my side now. First of all, we had organized to celebrate the World Space Week, we had organized a little competition, a satellite making competition. So the last date to submit your DIY satellite model is 17th of October, and next Sunday on 18th of October we are going to tell who won the competitions, and there are some gifts and surprises for you guys, those who win the competition and stuff like that. So do participate. Send your DIY satellite models to connect us at astronera.org. I just typed it out for you. So you can just email your images and information about the model there, and we will publish it across our social media. And I'm sure it's going to be so much fun, so do participate. Also, even though this is the last session by Reut, we are going to keep up with our live sessions, and we are going to have session by Ozgur from Turkey next Sunday. It's going to be about understanding and exploring the high energy universe. So all the doubts about neutron stars and black holes and supernova and the most interesting objects in the universe, he is going to talk about all of them. So I'm sure you guys will enjoy that. This is going to be a paid course, although the first session is going to be free for all of you to join. We are going to share a Zoom link with you. So those of you who take the advantage of the early bird, you can join in with him in the Zoom meeting. Same would be broadcasted on YouTube, but you can ask your questions in the Zoom meeting and not on YouTube. So I'll roll out the details, and all you have to do is fill this form up. I'm posting the link. I'll also post the link in the chat. Just fill this form up, and we will reach out to you with all the other details, and looking forward to see you in those sessions. Reut, you are receiving so much love in the live chat as well, and I'm sure everybody is gonna miss you. And I'm actually getting emotional. Like, it's been an amazing course, even for me, and I'm sure for everybody who's attended this. And I really want to thank you from the bottom of my heart for taking out the time for us and making all these amazing presentations, which made it easy for us to understand. And really, I mean, hats off to you, your research, your dedication, and you've really inspired us all. And I am extremely sure that most of us who have attended these sessions are looking forward to hearing more from you, getting more into astrobiology, and it's just been amazing. I cannot put it in the words. So thank you so much, and clear skies.
Clear skies. Thank you very much.
Okay, is it ended on YouTube? Everybody is so happy, like that. So much love for you.
Oh, well, they're a great audience. You got some really
Yeah.
big fans there, Shweta. That's good.
Well, actually, we are also receiving lots of messages and feedbacks on WhatsApp